Hey there, it's Shannon Magic-Myers, and today we'll be going over the logic of quantified statements. We're starting chapter 3, and we're specifically going to be covering predicates and quantified statements part 1. Time permitting, we will go back to the applications in 2.4 and 2.5. But as this is a new prep for me, I want to make sure that you get all the theoretical basis that you need. And I've also heard that you're able to make these connections in a lot of your computer science classes. So here we go. The symbolic analysis of predicates and quantified statements. Is called the Predicate Calculus. In the last 3 sections, we were examining the symbolic analysis of ordinary compound statements, called the statement or the propositional calculus. So in grammar, the word predicate refers to the part of a sentence that gives information about the subject. Consider the sentence, she is a water polo player. Is this a statement? What did we know about a statement? A statement either has to be true or it has to be false, but it can't be both, right? And so this one, we don't know enough about it. It's ambiguous, right? Because it could be true or false depending on the pronoun she. So let's check it out again. She is a water polo player versus Sierra is a water polo player at Valhalla High School. So if we kind of take a look at this one, and if we think of it as P being the whole statement, or the whole sentence rather, except for the subject. So if we look at this part right here, and we call this part P, capital P. And if we take a look over here and we just call the is a water polo player, we could call this one Q. So if we let P denote is a water polo player at Valhalla High School and let Q stand for is a water polo player at, then both P and Q are predicate symbols. And the sentence is X is a water polo player at Valhalla High School and Y is a water polo player at are symbolized as P at X and Q at both X and Y, respectively, where X and Y are predicate variables. That take values in appropriate sets. All right, so that brings us to our first definition where we're defining a predicate. So a predicate is a sentence that contains a finite number of variables. and becomes a statement when specific values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. All right, so let's take a look at an example. If we let p of x be the predicate, square root of x is greater than x, with the domain, the set, x, such that x is an element of the real numbers and x is greater than or equal to 0. So just a little bit of notation. This one means is an element of or belongs to, and you'll have to memorize these. The colon represents such that. Sometimes you're going to see it as a straight line. And then the capital R, I'm sure you've seen, represents a set of real numbers, right? So now what we want to do in this example is we want to write p of x and indicate if the statement is true or false. So in this case, what we're doing is wherever we see an x, we're going to plug in the first case 4, and in the second case a quarter. So here we go. P at 4, if we look at this one, that is saying it's the statement root 4 is greater than 4. Well, what do you think about that? I mean, if we evaluated the principal root of 4, we would get 2, and is that greater than 4? No, so we have a false statement. Okay? All right, over here, p of a quarter, the square root of 1/4 is greater than 1/4. Well, evaluating that, we would get a half is greater than a fourth, and this statement is true. So it may not be true for all x as we've seen, but it is true for some values of x. All right, good so far? Cool, cool. Let's go on to our next definition. If p of x is a predicate and x has domain D, the truth set of p of x is the set of all elements of D that make p of x true. So we're not ascertaining whether some predicate is true for specific values. We're finding the values for which it is true. And this would be called the truth set. All right. So the truth set of p of x is denoted. So you have this set x that is an element of D, the domain, given this predicate p of x. All right? So going on to example 2, let q at n be the predicate. N is a factor of 9. Please find the truth set of q at n if. So for the first one, the domain of n is the set of all positive integers. By the way, again, another shortcut symbol you want to know, that's capital Z plus. It's usually done in kind of a bold or fancy capital Z. So with this one, all right, well, what would be true? What is it to be a factor? Remember, a factor of a number will evenly divide that number, so you will get no remainder other than, of course, 0. So, all right, in the positive integers, which would take us to the counting numbers, remember 0 is neither positive nor negative. So 1, 2, 3, 4, 5, 6, 7, 8, 9. recognize that you can't go larger than 9, right? Because then that number won't divide 9. So what do you think? Beautiful. 1 divides 9, 3 divides 9, and 9 divides 9. These are the positive integers that divide 9. What if we're just talking about the set of integers? Well, you're still going to have 1, 3, and 9, right? But won't the negative of each of those, -1, -3, and -9, also evenly divide 9? So they would all be factors as well. Now note when you're using set notation that no order is assumed. So you don't need to go from least to greatest, etc. When you're doing a list of numbers in this way, right? But remember, in interval notation, it becomes quite important. Or if you're showing a, 1, 2, 3, that would become important. All right. So definition. Let Q of X be a predicate and D the domain of X. A universal statement is a statement of the form for any or for all X that belongs to the domain. Then Q of X, all right? So it is defined to be true if and only if Q of X is true for every X in the domain, every X. So no matter what, this predicate is true. It is defined to be false if and only if Q of X is false for at least one X in D. And this is where we come to counterexamples. They're very, very powerful in proof. To show that something is not true, all you need to do is provide a numeric counterexample. So a value for X for which Q at X is false is called a counterexample to the universal statement. Okay, so let's get another definition out there. This one is an existential statement. So if we let Q at X be a predicate and D the domain of X, an existential statement is a statement of the form. Now this backwards capital E means there exists. So there exists an X. There exists an X that is part of the domain D, right? Such that Q of X. It is defined to be true if and only if Q of X is true for at least one X in D. It is false if and only if Q of X is false for all X in D. So let's look at some more examples. Let R at M and N be the predicate if M is a factor of N squared, then M is a factor of N, with the domain of both M and N being the set of integers. So, okay, in higher math, like as we go on, we'll have to decide if this predicate is false or not. If this, if you're setting out to prove something or to disprove something, you need to figure out, well, do you think it's true or false? So a lot of times what we would do is just plug in some numbers, not always, 0 or 1, to see if it'll work. So if we take a look at this, well, M certainly is a factor of N squared, right? Because N squared would be equal to 100. And you see that 25 evenly divides 100. So that part's okay. But do you see that this second statement, this second argument, is not true because 25 is greater than 10 and thus not a factor, right? So 25 is not a factor of 10, which makes this whole predicate false. All right. Or at least not true for all, for sure. Actually, it is false because our domain is all of the integers. All right, so it's a false statement because we have found at least one that's false. So why don't you guys think about this one and do number 2. We want to give values different than what we just used for which r at m and n is false. All right, let's see how you did. I picked, well, if m is 40 and n is 20, 20 squared would be 400, right? And 40 divides 400, but 40 does not divide 20. And so those are my numbers for number 2. How'd you do? Great. All right, number 3, explain why r at m and n is true if m equals 5 and n equals 10. Well, 5 is a factor of 10, and we can look at it as 5 times 2 is equal to 10, and so thus 5 is a factor, right? Well, let's also take a look at 10 squared equal to 100. Well, 5 times 20 is equal to 100, so 5 is definitely a factor of n squared. And so I kind of did it in the reverse, but both of these statements are true, conditioned on m equaling 5 and n equaling 10. Good so far? Awesome. All right, well, let's find some other values different than we just used where this predicate is true. Beautiful. I used m equal to 3 and n equal to 6. Do you see that 6 squared, so our n squared would be 36, and 3 divides both 6 and 36, so we have another true statement. In fact, I'm sure there are infinitely many statements for which this predicate is true, but there are also infinitely many statements for which this predicate is false, and more importantly, there is at least one for which the predicate is false. Okay, so example 4, find counterexamples to show that the statements are false. So let's translate this. This is part of the difficulty, all right? What did the upside down A mean? Awesome. For any A, so for any or for all A, that is an element of the integers, very good. A minus 1 divided by A is not an element of the integers. So the upside down A meant for any. All right, well, counterexamples. This can be difficult, right? You're being told that it's false. So think about it. What about for A equal to 1, right? When A is 1, we would have 1 minus 1 over 1, right? Plugging in 1 for A, which in turn is 0 over 1, which is 0. Okay, A equals 1 belongs to the integers, right? And when we use that, we get an integer out because remember, 0 belongs to the integers. It may not belong to the positive integers, but it belongs to the integers. So we have shown via counterexample that the statement is false. Okay? So we have taken a domain value, in this case a is 1, and shown that we get a result which is part of the positive integers. Hence, this is a false statement. Okay, another infamously misused expression here, or equation. This is not equivalent, right? Cosine quantity x plus y is not equal to cosine x plus cosine y. Hopefully, if you're fresh out of trig, you remember that. So, counterexamples. Well, okay. If we take cosine at x plus y, and if we let x equal to, I don't know, how about pi over 6, and we could let y equal to pi over 3. So this would end up being cosine at quantity pi over 6 plus pi over 3, which in turn would be cosine at, so that would be 1 pi over 6 plus, remember, if you multiply by like 2 over 2, you get 2 pi's over 6. And then we would end up having 3 pi over 6, which in turn is cosine at pi over 2. And that, of course, we all know is awesome, 0, right? Alrighty. So this is what we are supposing for, both cases. So now let's examine the other one. Now let's examine the other statement here, the right side. So cosine at x plus cosine at y would equal to, given the same substitution, cosine at pi over 6 plus cosine at pi over 3. Cosine at pi over 6 is, great, root 3 over 2. Cosine at pi over 3 has an output of, beautiful, 1/2. And do you see that this is not equal to 0? And so hence these are not equivalent. So we have shown by counterexample that this is not a true statement. Groovy? Awesome. All right, so example 5. Rewrite the statement, all Akitas are dogs, in the two forms shown below. By the way, Akitas are a breed of dog, right? So there's more than one answer to some of these. So if we do this, all right? So if X is going to represent a dog, all right? So for any dog X, if what would we say? If X is an Akita, then what would we say? Awesome. X is a dog. Good so far? And again, I know that these can be a little bit daunting, but just practice, and you'll get much more used to translating math to English and English to math. Okay, so the other way. For any blank, X blank, all right? So for any awesome Akita, for any Akita X is a dog, right? Because all Akitas are dogs. Cool? All right, so now we get to, and by the way, this one here, this first one is what we did there, and then the second one was this one here. Implicit quantification. Let P of x and Q of x be predicates, and suppose the common domain of x is D. The notation P of x implies Q of x means that so this is, notice a double line on the flat part of the arrow, so that every element in the truth set of P of x is in the truth set of Q of x, or equivalently, for any x, P of x implies Q of x. The notation P of x, if and only if Q of x, with the double rows for the flat part of the arrow, means that P of x and Q of x have identical truth sets. Or equivalently, for any x, P of x, if and only if Q of x. Now, we see a lot of this in math that's implied that we don't think about sometimes. So whenever there's an equal sign in math, right, you have two, say algebraic statements equal to each other, or when you have two trig expressions equal to each other, then there are kind of, conditional, and there are kind of if and only if things. So let's think about this. I know how much you guys love your trig. So I'll just go ahead and do an algebra example. So let's take a look at this one. If we have, say, x squared minus y squared. Well, that we know factors as x plus y times x minus y. Good so far? So equivalently, what could we say? We could say for any real number, right, x and y, x squared minus y squared is equal to x plus y times x minus y. Now, I know in a lot of the, pre-calculus books or intermediate algebra books, they don't always say what number set these, are part of, but now it's very important to state this. So if something's in the real numbers, you need to say so. All right. Okay, so there's one. All right. What if you had something like this? Over here, what if we had something like, solve square root of x is equal to 5? I mean, what's really happening here? We're saying that show by finding a value there exists some x that belongs to the real numbers such that, so if you turn that around, it means such that the square root of x is equal to 5. And so this one here represents such that. Good so far? So this one here is an if and only if situation. Okay, so let's take a look at our last example. Then you can go enjoy the Super Bowl if you're watching it. Rewrite each statement without using quantifiers or variables. Indicate which are true and which are false. So here's our basis. Let the domain of x be the set of geometric figures in the plane, and let square at x be x as a square, and rect at x, rectangle at x, be x is a rectangle. So the first one, remember, this backwards capital E means there exists, it's existential, some x such that it meets both qualifications, right? It's both a rectangle and a square. So let's write that out in words, right? So there is a, because x, remember, was a geometric figure. And I don't know if you remember this, but by definition, a rectangle is basically two sets of parallel lines that cross, and they all are equiangular, right? But a square means that all the sides are equal. So a square is more special, but it still is a rectangle. So this one is indeed true. Okay, now let's look at the next one. Well, so there exists an x, so there's some geometric figure, there is a geometric figure, and now this one, which it's saying that it's rectangular but not square, right? So let's write it down. And so if you have a rectangle that has a height of 2 inches and a width of 5 inches, it's not going to be a square, but it is a rectangle, right? So this is indeed true. Let's take a look at this last statement. All right, so remember that upside down A means for any. So for any geometric figure such that it is a square implies it is a rectangle. Or such that it is a square, x is a square, implies it is a rectangle. So let's think about that. So remember up here with the implied one, it means that every element in the true set of the p of x, so in this case would be square of x, is in the true set of q of x, right? And so let's take a look. If you take a look, is it true that every single square is a rectangle? Yeah, it is, right? And we can write it like that. Every square is a rectangle, but the converse wouldn't be true, right? So just be careful on those. Okay, so that is indeed a true statement, right? So and again, just to clarify, every geometric figure that is a square is also a rectangle, right? Okay, well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this. And if you like what I'm doing, subscribe and feel free to suggest different kinds of videos that you may need for your math future. Bye.